Welcome to lecture 18. So in this lecture we will discuss methods for internal clock synchronization. So in this case there is no master clock or there is no global respected and acknowledged time base. So we have different processes with their internal clocks. We assume they are connected to each other. In the sense two processes have a channel to each other and then they can somehow decide on an internal clock, right? They can decide on an internal time. So how will they do it? All the clocks will periodically exchange their readings, and based on the readings, they will do something, right? So what will they do? So what they will basically do is that if the clocks periodically exchange their readings, then the clock will get a reading, of course, from itself, from C2, C3, and C4. It will average the times and set its new time to that time. So of course, it will do it in a in a gradual way, as we have discussed in the last lecture, such that time does not appear to flow backwards. All right. So, of course, some clocks could be faulty in the sense they could have failed completely, or they could be providing different values to different processes. So, some clocks can obviously age, bad clocks can exhibit large drifts, right? And so, then of course, you could have clocks from different models or different vendors where the manufacturers have prescribed different levels of tolerance, different levels of accuracy. But the point is that even if it's a good news if clocks keeps stop keeping time altogether, because at least then you know that the clock is not working, so you will not consider its input. But if a clock is deliberately lying in the sense the process has a virus or something and it has turned malicious, then of course it is a different problem, different kind of problem. So to handle bad clocks, what do we do? So what we can do is that we can look at the average of the system and the time that the bad clock is providing. See, if the difference is beyond a certain threshold, we can easily see that the clocks is most likely bad in the sense it has most likely failed or stopped. So any such time values that are received will be ignored. But a much more serious problem is caused by Byzantine clocks, which are malicious clocks that deliberately lie in the sense they give one value to one process and another value to another process. So a Byzantine clock, needless to say, is a malicious clock. So it can transmit different values to different clocks at the same time, which is something that we don't want in the sense that if clock C1 in this case is a Byzantine clock, it can transmit T minus E to C2 and T plus E to C5 both at the same time, which is not allowed, right? But given the fact that it is malicious, it can do that. So this is kind of where does the word Byzantine come from? There is a famous problem in distributed systems known as the Byzantine generals problem, where in a system you can say that if even if you have lying nodes, if more than two-thirds don't have these Byzantine faults, it's still possible to arrive at a consensus, where a consensus is some value that everybody agrees upon. So in this case, the time is the consensus. So how do you synchronize in the presence of the Byzantine clocks? So is it possible to even have approximate synchronization? Well, yes. Again, the same one-third rule applies. If no more than a third of the clocks are Byzantine faults, then it is possible to come up with an algorithm. See, assume that there are n clocks in the system, right? So we will have the standard terminology in this lecture that there are n clocks in the system. M out of those n are the ones with Byzantine failures or Byzantine faults. So again, fault and failures are not the same thing. A fault means some sort of a defect in a system, and a failure means that the defect has manifested in an erroneous output. So assume that the clocks are to be synchronized within epsilon time units of each other. So that is our that is our goal, our design goal. So when a clock receives a time broadcast, it checks against its own time. If let's say it differs by more than epsilon time units, right? Then most likely the clock on the other side has developed a fault, so it has slipped far behind. So that is why this time value is ignored. So after each step, the clock will basically take all the good values, right? Essentially, it takes all the values that are within epsilon units of its own clock. It'll average them and it'll use that value as its own time. So, of course, as I have said, just in case the clock appears to be slower, there is no problem, but it appears to be faster. It will not go back in time, but it will gradually adjust its time in the sense that, let's say, for every 3 milliseconds, it will add, let's say, 2 milliseconds. So, that is how it will progress. So, the synchronization in the process of Byzantine clocks, the algorithm is quite straightforward. So, assume you have n clocks. Initially, you assume all of them are good. You iterate through them. So, let's say if the time that is received, so I am clock I, right? So, the time that is received, the difference is greater than epsilon. This means that this is a bad clock. So, what we do is we decrement 1 from the counted good clocks, and the total time is made equal to total time plus Cj, where Cj is the time that a clock is showing. So, then in this case, Ci, so what is Ci? Ci is the time of the ith clock. Ci will be equal to the total time divided by the number of good clocks. So total time divided by good clocks. So here is a system. Here is a theorem. So in any distributed system with n clocks, a single Byzantine clock can make any two other arbitrary clocks differ by at most 3 epsilon by n. So we will prove this. But essentially, it is important to appreciate the statement of the theorem, which says that even if you have a single Byzantine clock, the maximum difference that it can create between any two other clocks is 3 epsilon by n, where epsilon is the maximum permissible drift between the two clocks. So we have discussed the epsilon term earlier also. So the epsilon term earlier was the maximum manufacturer specified drift. So consider clocks C1, C2 and C3. So we are looking at a proof sketch over here. So basically the internal time of C2 is C2. C1 tells it that its internal time is C2 plus epsilon. And there is an epsilon time difference between C2 and C3. And C1 tells C3 that its internal time is C3 minus epsilon. So now if you look at the time that C2 computes, right? So let's say the C2 new, that will basically be equal to C2 plus C1, which is nothing but C2 plus epsilon. All right. Plus the time of C3, which is nothing but C2 minus epsilon. Right. Divided by 3. So then epsilon and epsilon cancel. So this becomes equal to C2. But now consider C3. C3's time will of course be equal to C3 plus the time that C1 sends, which is C3 minus epsilon. All right. Plus the time that C2 sends, which is C3 plus epsilon. So again, epsilon, epsilon cancel out. So then you divide it by 3. So this becomes equal to C3, and C3 is nothing but C2 minus epsilon. So in this case, the difference between C2 new and C3 new is actually epsilon. And if we just go back to the previous slide, then the difference would have been 3 epsilon by n, which is nothing but 3 epsilon by 3 in this case, which is epsilon. Now what you can do is you can generalize this, right? So you can assume that there are a bunch of other nodes over here which don't have Byzantine faults. So in this case, this argument will slightly, this theorem will slightly change. In the sense, you'll have another term which comes from the rest of the network. You'll have n over here. You'll have another term which comes from the rest of the network. You'll again have n over here, right? So basically, then as you can see, the difference in this case. So basically, if I take n, so let me recompute. So in this case, C2 new will basically become 3C2 plus R divided by n. And in this case, this will become 3C3 plus R divided by n, right? Which is nothing but 3C2 minus 3 epsilon which is so the difference comes out to be 3 epsilon by n. All right. So this is exactly the proof sketch. This is what we are trying to prove. So let me now clear the clutter and then explain this once again. So what you can see is assume C2 and C3 are good clocks. So C1 is the Byzantine clock. So C1 is the one that is lying. It sends C2 plus epsilon to C2 and C3 minus epsilon to C3. Because of the Byzantine clock, the clocks at C2 and C3 would differ by at most 3 epsilon as we have just shown. And so in this case, after averaging C2 and C3, right? So basically, it's not that the clocks would differ. It is basically the sum of the values, right? It is essentially the sum of the clocks. So then if you average out the values for a 3-node system, the difference would be 3 epsilon by 3, which is epsilon. But then if you consider a rest bunch of other nodes where there are no Byzantine faults, then this will basically generalize to 3 epsilon by n. So this is the maximum difference that can be that can be created between any two normal and good clocks because of one Byzantine node, because of the fact that it is lying. And how much can it lie by? So essentially, it is lying here by the maximum in the upward direction. It's C2 plus epsilon. We're slightly more than that, and C2 will reject the value. And here again, it is lying, and it's lying in the lower direction as C3 minus epsilon. Again, slightly lower, and C3 will reject the value. So what is the explanation? So the explanation is that C1, the C1 is basically saying that it is C2 plus epsilon, and then there is again an epsilon difference between C2 and C3, and again an epsilon difference between C3 and C1. All right, so this is exactly the the way in which the values are being transmitted in the C1, in the sense that C1 tells C2 that it is actually C2 plus epsilon is its value. So this difference is genuine. And again, this difference is created because in the fact that the Byzantine clock is lying. It is not speaking the truth to both the nodes C2 and C3. So as we have seen in the derivation, if the sum at C2 is phi and the sum at C3 is theta, then their difference is bounded by 3 epsilon. And then if there are n nodes, then by averaging, the difference will be bounded by 3 epsilon by n for a single clock. So in this case, I am showing something quite similar, right? So this is very much in line with what we discussed. So here you assume that these are the values that are being exchanged. So in this case, instead of C1, C2, C3, we have C1, C2, C5, but this is exactly the same case. So in this case, C1 is the node that is lying. So C1 is telling C2 that C1 is actually C2 minus epsilon. C1 is telling C5 that C1 is actually C2 plus 2 epsilon. And given that C2 and C5 are honest, so the current time of C5 is actually C2 plus epsilon. So given the fact that the current time of C5 is C2 plus epsilon, it will not reject this value. It will accept this value because the value is just epsilon more than it. So it will accept this value. And furthermore, C5 is the largest between C2 and C5. So in this case, C2 is the smallest. So let me put the down arrow and let me put an up arrow over here for C5. So then what we do is if we just add up the clock values, so here we will have C2 plus of course C1 which is C2 minus epsilon plus C5 which is C2 plus epsilon. So the sum will come to 3C2 plus R, where R is the sum of the clocks of the remaining part of the network divided by N. And the sum at C5 would basically come out to basically be C2 plus 2 epsilon, right? So this is the value of C1, right? And then C2 plus epsilon, right? And then again the value that C2 sends. So if you see if you just work out the sum at C5 because of the values it receives from itself and C1 and C2 would be this, and plus the values received from the rest of the network would be the same. And again we divide it by R. So in this case we know, right, so that C2 is C5 minus epsilon. So what we do is that we subtract and then we add over here, okay, and so now if we consider the worst case, we take a look at this term R. So where R is the sum of the clocks of the rest of the nodes. So we can basically say that if we set R as n minus 3, okay, multiplied with C5 minus epsilon. So this will kind of be the lowest possible value of R, right? So it cannot be lower than that. Otherwise, C5 will start discarding the values. But given that in the rest of R, there are no clocks with Byzantine failures. So this will be their minimum possible value. So in a sense, I can have equal to or I can have greater than equal to, but I've written down the worst case. So the moment I add 3 with n minus 3 and then I add again this with n minus 3, so this turns out to be NC5 minus n epsilon plus 3 epsilon. So we will see in a second why did we convert this expression. So this expression, so let us just walk 2 steps backward. So what we did is we have one node with a Byzantine failure which is C1, and then we considered 3 nodes. And again if we consider the worst case, so the sum here will be 3C2 plus R by n. And the sum here will be the same 3C2 plus R by n, but we'll have this additional 3 epsilon term. And as I said, the maximum discrepancy between any two clocks because of a single Byzantine node will be 3 epsilon by n, right? So this is the maximum, divergence that you can have between two clocks. But then what we did is we tried to figure out the value of R, and we found out that for C5 to accept them, the minimum possible value is n minus 3 multiplied with C5 minus epsilon. So this is the lowest possible value that is permissible for R, right? Because lower than that, and C5 will start rejecting. But given the fact that the nodes are honest, there is no reason why C5 should reject. That is why this is the minimum possible value. And then we just rearrange the terms and we come up with this expression. All right. So now if we take the argument forward, so we now our aim is to compute the resynchronization period. So let us assume that we have m Byzantine clocks in the system, not one. So the time difference between them, right, between any two clocks because of m Byzantine clocks will be 3 epsilon by n multiplied with m, because every clock contributes 3 epsilon by n. And furthermore, right, if I take the rate of drift of every clock with respect to the UTC as rho. So what we have seen is we have seen in the earlier lectures that the maximum rate of the maximum divergence between two clocks in a period delta t can be 2 rho times delta t. So what we can do now is that we can set this term equal to, let me just go back and show you over here. See, equal to pretty much this term over here, and there is a reason I'm doing that. So let us again come back to this expression. So this is basically the difference. So basically, if you just go back to the previous lecture here, and you would find that basically this term over here indicates the drift of C5 with respect to the rest of the clocks, in the sense that if I just divide by n over here, so this would come to C5, right, minus n epsilon minus 3 epsilon divided by n. So insofar as we are concerned, this is basically the deviation of C5 with respect to the rest. So this is nothing but the correction factor. So here, of course, so if we consider m Byzantine nodes, the correction factor will change. But again, we will have, we will arrive at this equation. The reason is like this, that let us consider an ideal clock. Let us further consider the worst case, that C5 is drifting in a certain direction, which is above the ideal clock, and the average or the correction factor is drifting in another direction, in opposite direction of the ideal clock. So ideally speaking, if we want to correct the clock by this factor, it should be, upper bounded by the time that the clocks would have drifted, right, in a given time interval. So the upper bound of this is 2 delta t times rho. So the proof of this is in the previous lecture. This should be equal to the correction factor, which means that we will never drift by an amount which will lead to the divergence being more than the correction factor. Otherwise, we'll not be able to fix the system, right? We'll not be able to ensure that it is back to a state where the clocks are more or less equal to each other within epsilon. So this is a very basic equation in internal clock synchronization, where we equate 2 delta t times rho, which is nothing but the maximum drift between two clocks, where rho is a drift is the drift rate, right? And this is the maximum pretty much, and this we are equating with the difference between the system average and the clock C5 in our previous example. So if we consider this, so we will get delta t, which is nothing but the resynchronization interval. It is the interval at which we need to synchronize our clocks, as n epsilon minus 3 epsilon m divided by, so of course 2n rho will come to the denominator here, so divided by 2n rho. So to maintain synchronized time, what we claim is that the number of Byzantine clocks should be less than one third of the total number of clocks in the system. So if you see, this will basically come from here, that n epsilon should be greater than 3 epsilon m, and given that both are integers, right? So n has to be greater than 3m, or we can find that n will be greater than 3m plus 1. So 2 delta t rho will be equal to this. So given that n is greater than 3m plus 1, we will have this equation. We'll do a little bit of algebra. So this will tell us that the resynchronization interval, or delta t, should be greater than equal to epsilon by 2n rho. So the example is like this, that a distributed real-time system, let's say it has 10 clocks, up to 3 of them are known to be Byzantine. The maximum skew needs to be less than epsilon equal to 1 millisecond. This is the maximum drift rho. So the resynchronization interval is just given by this formula, which was explained over here. So if you just go back, it was explained that it will be greater than epsilon by 2n rho. So all that you need to do is have epsilon over here, right, 2 over here, n over here, right, 2n rho. All right. So again, there are a couple of practice problems, but I'll be skipping them. But you have gotten the key idea of having Byzantine clocks. So now I'm just skipping the quiz and the practice problem. So now we will discuss a few very basic issues in real-time operating systems. So now basically the part of real-time operating systems will begin. So we have to discuss the following things. The first is real-time priority levels and real-time scheduling, and support for resource sharing protocols. So one very important thing that we have been seeing throughout our discussion, both RMS as well as EDF, is that we need very low or very quick task preemption times because whenever a high priority task arrives, we need to preempt the currently executing task. So this has to be of the order of milli or microseconds. And furthermore, if there is any interrupt, so even a task preemption can be treated as an interrupt, it has very stringent and or very strict latency requirements. So then we need support for memory locking in the sense this can be a source of significant jitter. Here the key idea is that given a process, it will have its data in memory. We need to ensure or we wish to ensure that the pages are locked. What I mean by locking pages is basically that they remain in memory, they are not evicted. Otherwise, what will happen is if, let's say, pages are evicted from the cache or from main memory, to get them back, we'll incur a large latency, we'll incur a page fault, which is not really good for real time systems. Timers need to be well behaved, so we will discuss in detail what this well behavior means. And also, all file system support and accesses and so on need to also be well behaved. So the key idea is that when we are talking of anything stored on a device, be a network device or be it a file system. So in this case, what happens is that we don't want to send a request to an external hard disk, at least all the time, because the reason is that hard disk access times are very slow and they will introduce a significant amount of non-determinism into our system. So there, needless to say, has to be support for different real-time priority levels. Similar to RMS, have static task priority levels and also have a dynamically changing task priority as per EDF, right? So programmers should have the ability to assign a very high priority, a real-time priority to a task, and also traditional operating system should be able to run something very similar to EDF, where the priority is a function of the deadline. So as I said, it should allow programmers to also create their user land schedulers. So that is what they are called real-time task schedulers. If the operating system is not providing it, so we have RMS here and EDF. So many operating systems, kind of get out of the real-time game, right? Many modern operating systems, and they say that look, Windows has that if the user has some special requirements, then she can write her own scheduler for scheduling real-time tasks. Resource sharing, we have seen this, so there should be support for PCP for sure because PIP and HLP are not that practical, but PCP is definitely practical. So our aim would be to minimize priority inversions during the process of resource sharing. Next comes task preemption. So the RTOS real-time operating system task preemption times have to be very fast, preferably the order of a few microseconds because all our algorithms, be it RMS, be it EDF, are in a sense dependent upon rapid and very quick task preemption. So the worst case task preemption times for traditional operating systems are the order of a second. However, for real-time systems, we would like the task preemption times to be much faster, much faster, because otherwise we'll not be able to ensure that our tasks are meeting the deadlines. Interrupt latency is important in the sense that the time delay between an interrupt coming and its corresponding ISR and then the task again re-executing is important. So what a lot of operating system kernels do is that the moment there is an interrupt, they use that opportunity to deterministically run some of their own jobs, right? Do some of their own work. This is what they do. So it is important to rein in this behavior because if a real-time task is running, we should very quickly process an interrupt and again come back to it, right? So this is important. So the latencies have to be upper bounded and we are talking of microseconds. We're not talking of milliseconds. So that is why what happens in interrupt processing for real-time tasks is that we essentially divide interrupt processing into two parts, top half and bottom half. So the top half initially looks at the interrupt, and if the device itself has some real-time requirements, those requirements are satisfied. So then there is a separate queue called a deferred procedure call or a DPC queue. So there what we do is we schedule the bulk of the interrupt processing, which is the bottom half, which runs later. And at that point of time, the bulk of the work happens. But of course, this will happen with its own priority, which is different. So this may not have a real-time priority, again depending upon the interrupt. There is support for nested interrupts, right? Or let's say you need support for nested interrupts in the sense when you are processing an interrupt, if another interrupt comes, what happens? So then there are arguments on both sides. So the first is that if we support nested interrupts, interrupt processing will become fast. But again, there has to be means of storing the context of the current interrupt handler and restoring it later, which is not that easy. But at least what we want is that we don't want large kernel routines, whatever they may be, interrupt handlers or even otherwise, to be non preemptive. Then what will happen is that if there are real time tasks, they will wait because a kernel routine is running. And then once the kernel finishes, the real time tasks will start running once again. So we want our system to be as as preemptive as possible, such that the highest priority task always runs. For that, there is a need to re-architect the kernel, specifically the interrupt servicing routines, such that they support different degrees of preemption. Again, requirements from memory management, virtual memory is great. It has many features, most important being security, that two processes cannot overwrite each other's data. But most embedded real-time operating systems do not support virtual memory because the point is it increases the worst case memory access time quite drastically. So we have discussed this. The key idea is like this, that the moment we have virtual memory, we'll have the possibility of page faults and so on, of pages not being there in memory. So in that case, what will happen is that if there is a page fault, a lot of time will be incurred in fetching the page from the hard disk, right? And this is not really good for a real time process because it adds a lot of jitter. It is much better if the entire memory map is fully under our control and the memory access times are totally deterministic. So virtual memory, again, it does help reduce the average memory access time in a lot of cases, particularly when the amount of memory that we need is more than the amount of physical memory. But that said and done, virtual memory, at least nowadays, is seen more of a security feature and more of a correctness feature. So regardless of the amount of physical memory, you still need virtual memory. Otherwise, two processes may end up overwriting each other's address space. And page faults will also incur a very significant latency. So without virtual memory support, providing memory protection will become quite difficult. That's the reason you need it. But even if you have it, that's still not really a very good thing. Does any RTOS real-time operating system support virtual memory? Well, if you have large and complex applications, you definitely need it. There is no getting around it. But let's say if you also, want to support other applications such as text editors, web browsers, and so on, then also you need it. But let's say if it's a very small IoT kind of processor with very well behaved tasks, then we can possibly get around it. So, memory protection pros and cons. Well, if you have a single address space, it will result in very lightweight system calls. But if you don't have memory protection, the cost of developing and testing a program will increase, right? In the sense that you will have to ensure that all the correctness guarantees that virtual memory was giving are now being kind of coded up, right? Your new runtime is providing the same guarantees, which is not all that easy. And also the maintenance costs of programs will increase in the sense any new feature can break the system. That is why we will have to focus more on maintaining the program and the software infrastructure. Memory locking is the same idea where we just don't allow some pages to be swapped out into the hard disk. Again, this is fine if we have enough space, but if we don't have enough space, then there is, then this has to be done, right? So there is no getting around it. And even very critical tasks can suffer a large amount of memory access jitter because of this. Next, we come to I/O. So what we have traditionally seen is we have seen synchronous I/O where we you know issue a read call or a write system call and the process is blocked, right, until the operation finishes. But what may be more relevant in the case of real-time systems is, let's say, asynchronous I/O or non-blocking I/O. So in this case, what happens is that we issue a read system call, and then we go ahead and we do our job at least as much as we can. And once the result is ready, the operating system sends an interrupt. So we can again argue both ways. We can say that, look, if the interrupt overhead is high, the first approach is more efficient because at least you wait there and you get it. In the other way, you can argue that, look, if you are waiting, you are unnecessarily hogging up processor time. Some other task can run, and moreover, the idea here with asynchronous I/O is that it is non-blocking in the sense it quickly allows other processes to run while the data is being fetched or written. So in general, real-time operating systems will prefer asynchronous I/O, but then it depends on the I/O operation. So if the I/O operation is very short and very quick, we may go for synchronous I/O, but if it is slightly longer, then asynchronous I/O is the best. So this finishes our basic description of two concepts primarily. The first is the first was with regards to internal clock synchronization, and the second was with respect to the broad overview of real-time operating systems. So henceforth, our discussion will primarily focus on real-time operating systems in the subsequent lectures.